Yes guys, so this is the infamous Schrodinger's equation. You have two variations to it. One is a time dependent equation. You can see a t. You can find t in here. This is the shorter form of the very same thing. And this is the time independent, means you don't find a t in this equation. So it is not like at a specific time this is happening. So how does a time dependent and independent comes, that also we'll do a bit over here. As such, the fear of the equation is what I want to remove from you guys. One, we don't have to solve the equation at all. So if you skip all of this, still it doesn't matter. But since it is listed somewhere, and the human mind, if it is printed somewhere, you'll want to know what is what. So I'll just try to tell you what is what over here. I'll tell you what is I. What is I? What is I? It is square root of -1. So that's a complex number. It's not a real number, so there is nothing which can be squared and gives you a -1. A square root of -1 is I, and complex number as a whole chapter is going to come next to what is going on in your maths right now. So that's your I. What is this h bar? H bar is nothing but h by 2 pi. So it becomes convenient in writing this. You can write it as h by 2 pi. H as such is a constant. That's your Planck's constant. So this one has got another name to it, but you don't have to worry about it. Now what is this sign? What is this sign which looks like a D? So I'll come to that. That's partial differentiation of then this wave function. We have already done that wave function. The only thing which I think I did not tell you, now is the time to tell you that this wave function, it was a function, so it can take in variables. So it will take in the location of a certain spot in space and tell you what is the probability density at that location. Probability at a certain location is always 0. If I have say a dot on a meter scale, what is the probability that that dot I have put is at 30 centimeter mark exact? What is the probability? That's 0 probability of something being at exactly a point, because a point doesn't have a span. If I ask you what is the probability if I put a dot being in a space of say 35 to 36 centimeters, then you will say 1 by 100. In a meter scale, 1 meter scale, the probability becomes 1 by 100. That's your probability for being between 35 and 36. Being at 35, there is no probability, it's 0 probability. So you have to go at least a dx forward. So between 35 and say 35 plus dx, you'll have a probability of a very small amount which is tending to 0, is dx by 1 meter. So that will be the probability, but at a spot there is no probability. So this function is going to take in the values, the location of a certain spot. Get the point? And hence this function doesn't give you the probability, it gives you the probability density, meaning to say you'll have to go for a certain volume, then only it is going to give you a certain probability. So I'll come to that. First, the function can have if I have to locate a certain point in 3D, I can't draw 3D on the board because the board itself is a 2D thing. So the location is x, comma, y, comma, how much ever outside it is, that much z. So suppose it is a bit outside, then that much z, that's the location. So you can give the location of a point in the quantum space. You can give the location, and the whole thing I can write it in, instead of RT form, I can write it in the form of x, y and z. In fact, you can replace the r with the x to understand it better. You'll find it many places written in that form. The other way of going in a certain point in space is like in 2D. If I want to go over there, I can say that, I'll use another pen. I'll say that this length is r, which is in fact r square is equal to x square plus y square, is going to give that r if we are converting that x and y's to r. So it is at a certain point r, but R can be anywhere away, anywhere away. It has a certain point R at an angle theta with the x-axis. So that way you can locate it. Now if you want to locate it in 3D, then it is not enough. Your phi r theta will not be enough. So if you want to give another angle, say sigma, so it has not only gone up, it has come out of the plane, and you can give the angle with respect to the z-axis. So that's your z-axis. If it is coming out of the plane, it comes say 30 degree out of the plane. It comes 30 degree out of the plane. Then how much from the exact axis? 60 degree from the z-axis it is. So you can call this as that angle, which is, if I try to draw a z-axis, a 3D z-axis over here, your x and y and z is outside, mind you, z is outside, but just to show a 3D, say that's your z-axis, then the angle between the z-axis and that is this angle. So again I'll repeat this from this location, that's my origin, this is my location, that's the origin, that's your x-axis, that's your y-axis, and I have to go to this point over here, suppose. So what do? I first say I'll go r away. I've measured the distance, which is r away. R is the distance between the point and the origin. That's the distance between the point and the origin, that is your r. But then coming to the x-axis, I'll say first r I'll go from the x-axis, that's my theta, and then I'm going to come towards my z-axis from that xy plane. I'm going to come towards the z-axis, and the angle what I have to go is 90 minus phi. You could have called that as phi itself, but then there is easy conversion of xyz to r, theta and phi. In fact, you try to do that conversion yourself and it will be fun. Like in 2D, so r sin theta is your y and r cos theta is your x. So if you want to go in 3D, you'll go some amount up, and you can use your trigonometry to get that point also. So if you can see a 3D diagram and do it yourself, it will be quite fun for you. But I hope you have understood that with a radius and two angles, I can go to any spot in the space, or with xyz I can go to any spot in the space. So sometimes this is preferred because the calculations become easier when you are solving some complex questions, and this is not that preferred, but you can do any which way you want. So that's your phi, where it is taking the input in terms of your radial distance. So you can say for say theta 0 and phi 0, a certain equation has been written. Okay, you can change the thetas, you can change the r, you can change the sigma. So what I'm doing is I'm just explaining you each and every term. First I told you what is this h bar, before that I told you what is that I. Now what does this symbol, a fancy kind of D, means? It means partial derivative. So you have already done derivatives recently. So differentiation, partial differentiation of, say if I say what is the differentiation of x square, that's a 2x. What is the partial differentiation of x square? That's a 2x again. Now suppose I've got two variables. What is the differentiation of x square y by dx? I'll have to use the product rule or not, which will be y differentiation of x square by dx plus x square differentiation of y by dx. That would be the actual differentiation. But if I say what is the partial differentiation of x square y, what is the partial differentiation of x square y? So it means that apart from this variable x, it treats the other variables. Here it was a variable which is getting differentiated. Had it not been a variable, then this dy will come as 0. The dy comes as 0, the whole term becomes a 0. So in a partial differentiation, we assume that y is not changing. That means we are not deliberately changing that y. So y behaves like a constant, so it goes outside the differentiation and it will become a 2x and y. So that will be this answer. The y goes out of the differentiation and you differentiate only the variable which is changing, which is x. You don't change y, you don't change Say if it had a z also, a z also in it, then that will also not change, and your answer will be the differentiation of x square, which is 2x, and y and z will remain as they are. That is the meaning of partial differentiation. Now if I'm talking about x square y and I have to differentiate x square y, what I'm saying is I am changing the x, but I'm not changing the y. If I'm going from here, I'm going there. I'm going horizontally, I'm not going up, not going down, and seeing the gradient, seeing the rate of change with respect to x. So if I have to go somewhere over here, I have to go over there, I don't go directly like this. I go like this without changing my y, and then I do go like that without changing my x. So when I go like this without changing my y, I am doing a partial differentiation with x. When I go like this vertical without changing my x, I am doing the same differentiation. But that time I am doing with respect to y, and my x becomes a constant. X goes outside, and this thing becomes x square, which is x square again, which is x square only. Get the point? So we are doing differentiation of the function with respect to one of the variables, thinking that taking the other variables as constant. It is like going like this, going like that. So if you are doing that, if you are doing a partial differentiation, that's the symbol. So I hope you have understood what is partial differentiation. So here can you see what are the variables? You have r and t. You have r variable and t variable. So you are studying for a certain angle, you are studying this going the wave function with respect to variation in r and variation in radius and variation in time. So if I differentiate with respect to time, I'll consider my r as a constant and differentiate it. So that's that. What is this? M is mass. H I've already told, that's the negative sign over there. H bar square, it's a easier way of writing. You could have written a h square divided by 2 pi the whole square, which is a 4 pi square. So you'll get a 8 pi m over there, pi square m over there. Now what is this? That means del. I've written that over here. It is called del. Again, it is just a convenience. It makes our equation shorter to write and convenient to write. It means you are differentiating something twice. So yeah, I guess you would not be knowing this very well, that what does d2 a certain function y by dx means. So what is d2 by dx, say of x cube? What is d2 by dx? It is literally meaning this. It's a say a way of writing. You are differentiating the differentiation of x cube. So what happens is d of dx cube. So d and d comes 2 times. So in a way we write d2, and dx is there and dx goes at the bottom, and we'll write dx square. I'm sorry, I missed out the square over there. So d2 x cube by dx square means d of dx cube by dx. So it is a double differentiation. So like what is acceleration? It is dv by dt. What is velocity? That's a dx by dt, rate of change of x with respect to time. So what is dv? Dv by dt will be what? Dv by dt will be d of dx by dt. That was your v by dt. Now this looks little cumbersome to write. So you can write as d2x by dt square. A is your d2x by dt square, as simple as that. So that was a differentiation when there was one variable. If you have multiple variables but you want to consider only one variable is as the actual variable which is varying and the other two variables as constant, then you'll write this partial differentiation symbol. So the fancy D's. Okay. So this is not a number, nothing. It is saying that you're twice differentiating. So it is double differentiation of something, and that is in these three things. There are these three ways. So when you differentiate, you get what you get out of the function. You get your slope when it is a single variable function, y is equal to x. When it is happening in three variables, x as well as y as well as z, then it can mean various things like gradient itself. It can mean something called curl. So we don't have to worry about those things. We don't have to worry at all about those things. We'll just think of this as double differentiation, and we have to think, it is absolutely right to think of this as double differentiation of the function, whichever we'll be taking the function as, like del of x square y z. What does it mean? So it means double differentiation of this x square y z with respect to x, of x square y z with respect to y, of x square y z with respect to z. So what would be the first one? The first term, I'll not do all the terms, not required at all. So what is the differentiation? Yz first of all comes as a constant. X square differentiation will be 2x, but then it will be differentiated again, whose differentiation, 2x differentiation will be only 2. So we'll get a 2yz with the first thing. What will be the second term and the third term? I guess you have got it right, 0 and 0. You differentiate it once, you get 1. You get x square z and into 1. So that's a constant. You differentiate it twice, you differentiate a constant, you'll get a 0. So you'll get a 0 0 for this, and you'll get a 2yz for this. So that is the meaning of del. That's the meaning of del. So don't have to get scared that what it is. It's a simple thing. It is differentiating with all the variables, the partial differentiation. So that's the meaning of del. And what is this v? What is that v? V is your potential. It depicts, this totally will depict your potential energy. So that is giving your potential energy. So that's the symbol of v. So if you write the potential at a point, that's your v. That's your v here also. So I guess we have covered up all the things except for this whole big fat thing can be written as a single operator, Hamilton operator. So how is that coming into picture when he's solving that thing is coming into the picture? So what is a Hamilton operator? Hamilton proposed a certain parallel kind of mechanics himself. So that mechanics, Hamiltonian mechanics, gives you, if you apply the Hamiltonian operator, it gives you the total energy of all the particles in a certain distribution. So it gives you the total energy of all the particles. So this is, say, the Hamiltonian operator. This is the Hamiltonian operator. Then this stands for the kinetic energy and this stands for the potential energy. This is your kinetic energy part and that's your potential energy part. Now if you go to quantum physics, then this is what Schrodinger worked out. It's not like he's assembling just everything. If you go to quantum physics and you calculate the kinetic energy, then this is what is going to come for a distribution. What he is thinking, that the charge itself is smudged and distributed, and he is getting the total energy of that. I hope you got that point. He thought that charge itself is dissolved in a certain space. One E is dissolved and it's a party over there. So that wave thing for him is like a bit of E here, a big bit here, a small bit here. That E is itself distributed, and what he is trying to get is all that distribution is having how much of kinetic energy and potential energy. As simple as that. So he is getting the total energy of that distributed thing, and on doing it for a quantum particle, he gets this. So it's not like way far off from the momentum equation what we already know, what Bohr got it. So he's getting through pure maths, by the way. So he's getting it by doing that standing wave thing. And if you remember the momentum, what Bohr got was angular momentum, which is momentum times r, was nh by 2 pi, right? nh by 2 pi. Now h by 2 pi I can call it as h bar, right? So this t part, this kinetic energy part, is it like p square by 2m? Let me just ask you, is it like p square by 2m? Momentum is m square v square, mv is your momentum, m square v square by 2m, one of the m gets cancelled, it gives you half mv square kind of thing, right? It is a simplistic way of looking at it. We have it has to be in a vector form, and then we have a dot product with a p and a p, but just to give you a notion, so it is giving you half mv square or not, because the p is mv. Get the point? Now if p square by 2m is your t, then if I say p square by 2m, so what do I get over here? What is p square? P square is h square by r square, right? I get a h square by r square by 2m. So we are getting that kind of thing over here or not? We are getting that kind of, with a r square at the bottom, but we have further things in this. We have to differentiate them something. So we are getting near to that. Now this is ratifying your Bohr's model. Bohr, you can say, he just proposed from thin air that angular momentum has to be quantized, which is this. Angular momentum has to be quantized. It is coming quantized because of this. It is actually coming quantized with its variations because of this. So just what you have to take home from here is the Hamiltonian operator gives you the total energy of a distribution of particles, where this stands for kinetic energy and that stands for potential energy. So this guy in quantum physics is what Schrodinger found out. This is the big thing. What he found out is your kinetic energy. That is the kinetic energy contained in that quantum space. That much of energy is there in the quantum space. Get the point? So if I don't have to write these two things, if I just want to shorten and write, del square itself means nothing. Why? Because if I say d of dx, what does it mean? You have to put some function over here, which is what you are going to differentiate. So what is the thing which is getting differentiated? This thing is getting differentiated. So I could have written this over here and then this with this. So both of them, so this is getting multiplied with this and this is getting differentiated over here. It is like this. That differentiation of phi, and then v is getting multiplied with this. So that is this. So you have put the Hamiltonian, I have bracketed it and written so that we can call this as Hamiltonian operator, and this Hamiltonian operator has been put on that phi. So that is how it is written. So your left hand side remains as it was. You can write the variable on which it depends, and here also variable on which it depends, and the Hamiltonian operator. So it is not a multiplication. So if I say sine theta is equal to, say, theta by 10 for a certain angle, then theta gets cancelled and sine is equal to 1 by 10. Sine is equal to 1 by 10 is absurd. It is nothing. That's crap. So don't cancel out the phi here and the phi here. This is a differentiation of something. This is also a differentiation of something apart from other things. So you can't cancel out. It is an operation over here. It's a double differentiation of that thing plus the v part. At times we write the v part on the other side also, so that it is only differentiation on one part. So that is your time dependent equation. So time independent equation is also having the same similar terms, and here what pops up is the energy. That is the other term which is coming over here, which has not been described in this. So what is coming over here is good for us, energy. That gives you the total energy. So in a very short form, in a cute way, we can write Hamiltonian on the wave function is energy times the wave function, is energy times the wave function. Now how are you getting that? How are you getting that? What is a time independent thing? How we are getting is, math is not required. What is a time independent thing? So it's not a big deal. They just figured out how to remove time from the equation. Like if I say x is equal to a sine omega t, I'm just going back to our initial example, and say a velocity will be differentiation of this with respect to time. So what will it come? A, that omega will come outside because you'll differentiate with respect to omega t, and then omega t with respect to time using your chain rule. So a omega cos omega t is what is your v. Now suppose I want an equation which is a time independent. I don't want time, I don't want to look at time in the equation, and I want a connection between the stuff. Omega a, t and x is connected. I want, and from there I am deriving v, but I want to get the relationship between the variables, say x and v, without the time. So what I say is, I say that sine omega t and cos omega t, if I square and add, it is after all the same angle, whichever angle it is. So if I square and add, it is going to be 1. So what do I get is x square by a square plus v square by a square omega square is equal to 1. So that becomes a time independent equation, right? Mathematically it becomes a time independent equation. Now what can it physically signify? So this physical significance will be doing these equations in your SHM chapter, and you'll be doing it. It's like hardly a minute job for this to do and to understand, so not a big deal at all. So what will it signify? Like time independent and time dependent will have a bit of explanation going on. Like if I put a external magnetic field onto the quantum space, then what happens? I don't want to get into that. I just want to explain this equation to you. So what we have done is, we have dissected on each and every part. I have told you what it means. Potential, the wave function itself. The wave function was a certain calculation which was coming. Let me show you something which will give you an insight of why this kind of calculation is coming. Like you have a certain operation on x, on a variable, and it is giving you e times the variable itself, where e is a constant. Mind you, e is a constant for that quantum space. This is the e, and we are going to find with so much of energy what is the wave function solutions. We'll have various wave function solutions with a constant e, and we can vary the e. Like this energy, these are the wave functions. With that energy, these are the wave functions. So we'll do that later. So that is what it means with a constant e, the various solutions what it can give. So it is a damn complicated equation. So it gives you various solutions. I'll give you a damn easy equation what we are going to do, and its solutions of a similar format. d2x by dt square, that means double differentiation of x with respect to time is, say, minus some constant, say omega square is a constant, into x. How does it look like? Does it look like similar stuff? Double differentiation of this, that Hamilton was in fact Hamilton for a free space, for free electron not having any influence of external electric field. Your V becomes 0. V becomes 0 for free particle. So if V is not having, if there is a electron which is not confined in, say, atom, it is just moving freely, then very nice diagram, very nice representation. You can see the animation. This kind of wave is just going. It is not an electron. You can say that the electron is a pinpoint object which is going in this line, but that wave, that smudged out thing, it is a smudged out thing which goes. You can say that most probably it lies here because the amplitude is more, most probably the electron is there, but it can be anywhere over there. That's the uncertainty. You can't for sure say, and not because of limitations, because the actual fact that it is uncertain where it is. So that's your wave which is going for V equal to 0. For V equal to 0. So if I say V equal to 0, it's a double differentiation, a constant and a double differentiation. A minus will come over there, right, because of the minus there also. So suppose minus was there or not there, whatever, because E itself is minus and then it will become plus. So I don't want to get into that minus plus thing right now. I'm just saying that a double differentiation of something is giving the same thing, right? Now is how to solve this in your math. In a year's time, again, you'll be solving it. Unfortunately, you have to look at the solution right now so that you understand why this all stuff came. So if I solve this, I'll propose a solution. I'll not solve it because it's a differential equation to be solved, which is a whole big chapter. If I propose a equation which is same as what I proposed earlier, a sine omega t. Now you see whether this matches or not, whether this thing left hand side is right hand side or not yourself. You can pause the, I got disconnected. So what I was saying is, what we are seeing that a sine omega t is figuring again after differentiating twice. So that a sine omega t, if I replace with a x, what we get is, we get d2x by dt square is equal to minus omega square, which remains, and x instead of a sine omega t. So is this solution not very similar to this one? That's again a double differentiation of a certain function. Now that is a variable, okay, that like this is a variable. It itself depends on what all things is another story. It itself depends on r and a theta and a phi and a t. It's another story. So this math is working all right. So this function itself is giving these kind of variations. If I conclude that this is the solution to that, then it is, but it is not the solution because it's not a simple solution. I have just made a assumption that your V was 0. First of all, your V was 0, and then with the minus and plus, I have just played a trick because even if I don't do this, I'll leave it on the board for a while so that you can understand. And if I had proposed again a double differentiation of something is a constant into the thing itself, and I propose something like x is equal to, instead of x is equal to, this was my proposal, right? First proposal, right? I'll give my other proposal in red. X is equal to e power, say, omega t. E power omega t. Now what do you get? What do you get on differentiating? Dx by dt is equal to, omega comes in front and e power omega t again, right? So first of all, my dx by dt is w times is omega times x itself, but I want a double differentiation because this guy is a double differentiation. So I'll double differentiate and I'll get another omega in front, omega square e power omega t, which I can write as omega square x. So again, my solution that d2x by dt is equal to omega square x is somewhat similar to this. This was having a minus, this is not having a minus in it. Okay, now the wave which comes out as a solution is somewhat of this format. And if you remember what I said about the wave, if it has to be a wave, which eventually will superpose and form a standing wave, then it has to have a component of omega t minus kx in it, right? two things, time as well as x, time as well as x. So this is that kind of equation. This is that kind of wave, and in fact I'll write a plane wave which is giving you the format. And let me go one step ahead and tell you that I wanted this negative kind of solution, that minus omega square has to be there. Then this is the solution and not this, because this gives me a plus over here. Then I propose that is this omega itself, or I had a I attached to it. I had a, instead of omega it was a I omega. Suppose it was I omega t, e power I omega t. What happens? In the last step you'll get your I square omega square and the x again. Now I square, as I told you, I is under root of minus 1, I square is a minus 1 and a minus will come over there, right? So shall we go for this solution or shall we go for this solution which has complex component? So the thing is, if everything has to fit in well, then it comes as a complex solution. It doesn't come as a real solution, it comes as a complex solution. And what can those complex terms mean is still being debated. What can be the physical significance of all these terms? But this is a mathematical solution out of which we can find out whatever we want to know, whatever information what we want to know of that quantum space with respect to energy, momentum and stuff like that, magnetism. So I hope you have got a good clarity on what it means, what it all means. And now let me write down the Schrodinger equation for a hydrogen atom. Let me write down the Schrodinger equation for a hydrogen atom. So this is like, it will hold good for any space, any quantum space. And hydrogen atom, we have potential also, right? We had done that while we were deriving Ohm's law. At a certain radius you have a certain potential, and the potential energy was given by something. So the formula of potential was minus kq by r, if you remember, where k was 1 by 4 pi epsilon naught. So it is not like v was 0. So we are going to write down, and let me write down in this format, the time independent one, and v comes on this side. Suppose I take the v on this side, what does it become? This is v is not an operation on that, this one is an operation on that. This is a simple multiplication. Potential into the into the particle, which is like a wave function. Okay, nobody knows what the particle is. It's not a particle, it's a wave function. So v into the wave function. Generally v into the particle gives you the potential energy. Okay, potential into the particle, potential into q is the potential energy of the charge, potential into mass is the potential energy of the mass. So but don't worry, the SI units will satisfy. So this, if I take on the other side, what does it look like? It looks like, and this also, this is a minus, I'll take on the other side. So what will it look like? Will it look like this? Shall I write in 2 steps or a single step? Shall I write it in 2 steps or a single step? I'll just write it in a one single step, because some of you would be, by God, if none of this is going to come, then why all of this? Okay, so I have written this, I've taken it on the other side. So minus reduced Planck constant, h bar is called reduced Planck constant, did I mention? And there's another name to it, starts with the D. So if I take it on the other side and cross multiply 2m and the reduced Planck constant square, then what will I get is, I'll get right. I'll just emphasize on one thing which I think I did not put too much of emphasis on. When you have solved the Schrodinger's equation, when you have solved this equation, you are getting the wave function, you're getting some wave function. That wave function is several solutions, it is not necessarily one solution, and the solution is having the quantum numbers what we know, L, M, L, N and M. These quantum numbers are the natural consequence of the solution of the wave function. It is not because the energy comes in quantums, it is ratifying that. It is coming to the conclusion that is also getting ratified, but this, on just solving the math due to the standing functions, you are getting the solutions which are jumping in integral values N, L, M. If you keep on tweaking them, you'll get different solution. You'll understand that more when you have done this standing wave on a string. Like, let me just draw. On the string I can have a standing wave like this, or like that, or like this. You do whatever, and if it has to come to a stable state, then when you are doing with the string, I hope you see the video, either you'll get this or this or this. So you get a 1 balloon, I would say, or 2 balloons or 3 balloons. You don't get a 1.5 balloon, 1.8 balloon, 2.3 balloons. You don't get that. You get either this or that or that. You have your nodes formed. You have your nodes formed and you have your antinodes where it is the maximum amplitude, meaning to say where the probability of finding the electron will be maximum. So this solution of the standing wave itself is coming in quantums, right? Either 1 balloon or 2 balloon or 3 balloon. So that kind of solution is these numbers which are coming out, which I already told you, they are all interlinked. You can say all of them are linked with N. With the N itself you can dictate your L and then your M. So you vary those numbers and you will get your different energy levels, or you will get your different angular momentum, or you'll get your different orientation if not the angular momentum varies. So this is what I wanted to tell you, that the solution of this is giving those integral numbers. That change in integral number, you put various integral numbers, that they are giving you the various solutions. So that's a natural solution of the equation. It is not like we are taking the energy in quantum. So if we back calculate, then energy comes in quantum due to this solution. So I hope you have understood. At least you understand this thing, that if it has to be standing wave, it has to be 1 or 2 or 3 or 4 or 5. So that kind of solution is to the equation. Later on it was interpreted that it has been correlated, everything has been correlated, the quantum physics, the quantum mechanics, the gain of energy in quantas, so that everything has been correlated, and this equation stands like a firm pillar, as good as F is equal to ma in classical physics. This equation, Schrodinger's equation, it is irrefutable.